Uh, this is my code. It looks a little bit more complicated than the code from Monday's class. It's the same Markov chain Monte Carlo. So that bit of the code is really very similar. There's maybe a little bit of more complication associated with the calculating the interaction energy between the neighboring dipoles. So that's where it probably looks a little bit more complicated. I tried to pull out some distinct pieces in the code into different cells. Okay, so I obviously, again, I've got to get NumPy and Matplotlib. This cell here. So this cell here, if you look in here, all I'm doing is defining 3 user functions that I'm going to use later on. And so in a way, you can just look at the names of these user functions too, and later on, I'm just going to call them to do what the name suggests. So the first function, initial state. So later on in the next cell, I'm going to call initial state to generate an initial state of my 100 dipoles in a 10 by 10 array. And I'm going to generate the initial state. It's really just going to be a 10 by 10 array of +1s and -1s. So the +1s are the ups and the -1s are the downs. And I'm just generating it with integer random number generator from NumPy. That's in this one line here. So just to explain how it works, so in this random integer generator, this function here, these first 2 arguments specify the range of integers that it's going to generate. So it starts, I never really like this, but it starts from 0 and goes to 1 less than the second argument. So here I can just generate 0 or 1. And I'm going to generate 0s and 1s in an array that has this size, n by n. Now, n is an argument I'm passing. It's going to be the dimensions of the kind of crystal or the lattice. So n is going to be 10. So the outcome of this function call is going to be an array of 0s and 1s in a 10 by 10 array. If I multiply it by 2, so make it 0s and 2s, and then subtract off 1, I'm going to get an array of -1s and +1s. So that's my initial state. Okay. Calc energy. So this is going to calc the magnetic energy. And this is really the heart of the Monte Carlo, just like calculating the internal energy on Monday was the heart of the Monte Carlo there. So when I call this, I'm asking it to calculate the magnetic energy of the lattice. And I'm going to call it with 2 arguments. One argument is the J, which is the interaction strength between neighboring dipoles. That's just going to be convenient if I want to change the interaction to explore it. And then the other argument, the config, is the current microstate configuration. So it's another array that is continually changing as we change the microstate. So it's again an array of -1s and +1s, but it's the array I keep updating. Okay. So so this function is going to calculate the energy of this particular microstate for this 10 by 10 lattice. So the way to do that, firstly, I initialize the energy to be 0. And then ultimately, I'm going to return the calculated energy down here. But inside here, I've got this pair of nested for loops, which, basically walk along the rows and walk down the rows and walk along the columns to every atom for every dipole in the 10 by 10 array. So that's what the the two nested for loops do. This quantity length of the array, this is maybe a little, I never like this too, really, in a way. So if you ask the length of this 10 by 10 array, you call the length function with the 10 by 10 array as the argument, it's going to give you the number of rows, actually. It doesn't give you the number of elements. If you use size, it will give you the number of elements. But if you give it length, it'll give you the number of rows. So it's just going to be n. I mean, we really could have used n there. That would have probably been clearer. I think it was just history. So this is why, you know, this is going to go over all the rows and all the columns. That's essentially what I'm doing here. Okay, so for the 100 times I go around this loop, I'm going to grab the state of the dipole that I'm thinking about at location ij. And then I'm going to grab the states in this sum of the 4 nearest neighbors. So again, you know, to find the state of the dipole ij, I'm looking in the array with the macro state at the location ij. And to find the configuration of the nearest neighbors, if you look at the arguments in here, I got an I plus 1, j, I got a I minus 1, j, and I've got an I, j plus 1, and an I, j minus 1. So those are the 4 nearest neighbors. And so I'm adding up whether they're ups or downs or whatever. So S is simply whether that one dipole for this particular path through this nested for loop is up or down. And then the neighbors variable is the sum of the 4 nearest neighbors. There's one little subtlety that's sort of important in these calculations. You see this guy here, the modulus n on all of these. So why did I put that there? Supposing, imagine the rectangular array. Supposing I'm right at the top of it. My nearest neighbor is below, left, right. Oh, I try and go above. There's nobody there. That house is empty. Now, one way you can solve that problem is spot that in your code that that's happening and just say that that's 0, right? That would be like modeling, truly modeling a 10 by 10 array. And you would have significant edge effects because, you know, because it's just a 10 by 10 array, there's a lot of edge. More realistic, right, in terms of exploring magnetization is to think of the 10 by 10 array as really just a tile in a much more massive array of kind of copies. So when we go up to look at that element that isn't there in the 10 by 10 array, if we take the modulus, it uses the neighbor of this guy above it as the one at the bottom of the array. And likewise on the left and right and the bottom. So that's the purpose of the modulus. So that is kind of a boundary condition that I'm imposing on this calculation, and you could do something else. Okay.
Would that not double count?
Yeah. So that's a really good point. You actually anticipated. Look, when I calculate that's exactly right. It would double count. So if I just multiply S and neighbors, you know, for every ij, I'm going to have a ji. So I have double counted. So I have to divide by 2. Yeah. You can divide by 2. You could also, you could change the range of this nested loop too, so that you don't double count. But I think it's simpler to put that. It's more obvious if you put that 2 down here. Anyway, we come out of this calculation then after we summed up all these magnetic interactions with the total energy of the lattice, magnetic energy of the lattice. So that's going to be a really useful function. The last function in here is pretty simple. So like this one calculated the magnetic energy, this one calculates actually the magnetization. So what is the magnetization of the lattice? Magnetization of the lattice in the units of magnetic dipoles is just the sum of the ups less the sum of the downs. So it's just like add all the elements of the microstate up, and the minus ones will cancel the plus ones, and you get the net magnetization. Okay, this next cell, I just want to initialize my lattice and just show you the lattice that we're starting from, so that we're all okay with that. I'm going to initialize the lattice, the initial state, and I'm also going to define the interaction energy, and I've just made it KT. And so calling initial state just generates this random array of plus ones and minus ones. Here is the array, and here is the a depiction of the array as these tiles, right, where the magentas are the downs and the yellows are the ups. And so we got our initial state. So that was easy by calling that function. And then the whole calculation of the magnetization is in this cell here. And this cell really looks almost identical, or at least very close to the corresponding cell in the quantum gas problem from the Monday class. So I define two lists, a list in which I'm going to track the energies as I walk through the microstates, that's EI, a list in which I'm going to track the magnetizations as I walk through the microstates, that's the MI. Once I've initialized them, all I can do is append the starting magnetization and append the starting magnetic energy. So that's the initial values of E and M. And I get those by calculating the energy here, calling that calc energy function, calculating the magnetization here, calc mag function. Then I'm going to do the random walk, and all the random walk is down here. So I'm going to pick a number of steps to walk. I might have to adjust that because it might be not enough to burn in an equilibriate, or maybe it's way too many. I don't need to do that many. Anyway, so I pick a number of steps, and we're going to go for that number of steps in the random walk. Here, these two lines, I got to pick a dipole in my array of dipoles that I'm going to toggle. And so I'm just randomly picking an I and a J, and I'm going to use that as the coordinates of the dipole that I'm going to flip the spin, flip the magnetic moment. So I get an I and a J. Once I've got the I and the J, here, what do? I calculate the magnetic energy. I calculate the magnetic energy, or the system energy, for the original configuration of the microstate. I then flip the microstate, flip the dipole in the microstate, and then calculate the new magnetic energy of the microstate. So that's what you see going on here. This is the calc energy call for the old energy. This is the calc energy call for the new energy. And look, this is where I'm flipping a spin. To flip a spin, I just got to multiply that particular dipole by -1, because it's going to, if it was up, it'd make it down. If it's down, it's making it up. So I've done that. Remember, we had this accept or decline criteria. That's where the Boltzmann factor enters. It's where our understanding of thermodynamics really enters, and that's done in this if statement here. So this if statement is such that if either the energy went down, then I'll definitely accept. Okay, so if the energy went down, I'll accept. If the energy went up, I'll accept based on comparison to the Boltzmann factor. And so That's what's happening in here. If I try and increase the energy and trying to increase the energy by too much, then I'm likely not to accept that step. If I don't, so let me be careful about this here, because maybe this is confusing the way I did it. Maybe this isn't a very smart way. I've already flipped the spin. I already flipped it because I had to calculate the new energy from the old energy. So if I'm not going to accept it, I want to flip the spin back. I want to undo what I did. So this if statement is true if I'm not going to accept. This if statement is true if I'm going to reject. If I'm rejecting, I'm putting the spin back where it was. So that's why it's like that. Okay, well, once I've done that, I already have the, I basically calculate the magnetic energy here. So at that point, I have taken my random walk. I've followed the energies, the magnetic energies, and I've calculated the magnetization, and they're in these lists. So let's just look at the data. So I got two plots here. Let me show you these first. I didn't expect that. Let me go down here. Oh yeah, I see what, actually I got an interesting case, more interesting than I thought. So this first graph here, if I'm plotting the magnetic energy. And then on the second graph, I'm plotting the magnetization. And then on the third graph, I'm plotting the you know, the ups or downs of the individual dipoles. So you actually see an interesting thing in this plot. It looks like I have magnetized the material, but I've got domains in the material because I got this domain that is mainly downs and this domain that is mainly up. So I've actually got an interesting situation here. So I will have a magnetic, non-zero magnetic energy because not just randomly ups and downs. I will have an overall magnetization because my domains are different sizes, but it's not the maximum magnetic energy or maximum magnetization I can get. Now, maybe this is not so surprising that I'm sort of in this region where J was KT. So the magnetic energies and the thermal energies was similar. So I'm really there. The two of them are really battling out. Let me show you another couple of cases. Let's go back up here. Let's make this 10 times smaller. So I generated another random state. So to begin with, then I'm going to do the random walk. And then I can make my plots again. First one, magnetic energy. Second one, magnetization. And third one is the microstate. And so now you see there is very, on the scale of the previous case, there's very little magnetic energy. So there's hardly any ordering. I mean, there may be some ordering because I use 10% of KT, not 0. So there's very little magnetic energy. There's very little magnetization, sort of statistically, it's kind of in the noise. And then when we look at this plot down here, we see, you know, kind of a more random array of ups and downs. If I went up here and did, let's try one more. So let's make the magnetic interaction stronger. Let's carry out the calculation. Yeah, so now turn the magnetization up. And actually, if you look here, I've locked in, this must be, you've got, each dipole interacts with 4 neighbors. You know, if there's, but we've got to worry about double counting. I think the energy is going to be more than, the maximum energy is more than 100, right? That would be, you know, if you just, more than 200. It seems to be 400, which maybe there's some double counting here with the interactions with the 4s. But anyway, we've approached kind of a maximum magnetic energy that is really stable here, right? It's not fluctuating. We completely magnetize the array. We approached, this one is a better one to look at for the maximum value. The magnetization is 100, right? Which means that every one of those dipoles is lined up. So that makes sense. And then when we look at the array itself, they're all downs.